So we'll move on now to evaluation. We've classified our data using one method or another, whichever method we've used. We now need to evaluate it. How good was the classification? So the first thing we can do is something called thresholding, and that gives us a feeling for what the data, how things have behaved. And then we can do something called accuracy assessment, which gives us a number, so to speak. It gives us a way of actually specifying how good our work has been. But because of the work involved in accuracy assessment, it might be better to start with thresholding to see whether you might need to just run the classification again in a different manner. So thresholding, this begins by using a concept where we look at the distance in band space. So just exemplify this. We have our seed here. Let's say that this is the result of a classification, and we've got this seed, or the class center, I should say, not seed, class center here. This is our final result. All of these pixels have been classed to that pixel, but we can see that there are different distances from this mean point. So that's quite a long way off. That one's quite close, but there's this distribution of distances between them. And it's a similar thing here. We can see that there's different distances for all of these pixels from the mean. There's a distance in band space. And this concept we can continue out to all of the different classes here, but let's just take that as read. And then from that, we can create a new image. We can go back to the spatial arrangement, but instead of showing the colors that were registered originally, we show this distance to the class space. So instead of the red, green, blue, infrared, we have a grayscale image where the intensity is equivalent to the distance of that pixel from its class. It's been classed, and how far away is it from its classed center? So how close to the average value is it? So the dark pixels, they're close to the center. They seem to be much like the average value, or the true value, as it were, for that class, if that's what we have. Whereas the brighter pixels, they're a bit farther away. They're a bit more ambiguous, perhaps. The classification is perhaps less true for them. That's difficult to say. It's not necessarily the case. It could be just as true. It's just that maybe we've got a larger spread in the class. But we can also examine this not just by looking at this distance image. We can also look at histograms of that distance image or of the data set to look at how they vary. So if we look at the histograms, there are 4 different types here, just to cover some basic problems that we might have, or things we might need to consider. So in this first case, which is actually a pretty good case, most of our pixels are pretty close to 0 here, so they're tight into that center. That's good. That's what we expect. But there is this tail sort of coming out of pixels that are a bit farther away and a lot farther away, and maybe we should consider cutting off. Maybe those ones out here, depending, we don't know, but maybe these are not properly classified. Maybe they should have ended up in a different class, or create a new class for them. Depends, we'd have to examine further, but we could maybe consider that. If we move down to this next, we can see that things are getting a bit problematic here. We've got we've got problems here. We've got these bumps. Why are we getting clusters of pixels here? Things start to get a bit shaky, and when we sort of extend that even further, well, we've got a so-called multimodal distribution. There's also another problem we're going to show in a second. The multimodal distribution means that actually we've got several classes in our one class, because it seems as if there are clusters of pixels. It's difficult to say, because of course this could be rings in band space as well, which would make things really difficult, because this is just the distance from the average of the class, but probably not rings. It could be, but probably not. So it's likely that we've got different classes of data. And we need to reclass. We've missed somehow we've managed to miss these classes. And then the last problem, which probably should have come in second place, just because of how the other graphs look here, or the histograms look. When we look here, we can see that actually most of the pixels that were assigned to this particular class weren't really particularly close to the middle. So this average, they ended up somewhat away from it, which suggests that our initial training area perhaps wasn't terribly representative. And if it wasn't terribly representative, then, well, maybe we've missed some other things as well. So when we look at this distribution, this is all should make us think. Perhaps we need to redo the classification, find a different training area for this class. Maybe that wasn't quite right. So these are ways of assessing this. And all we've had to do is just to make this distance image, check the histogram for each class. What does it look like? See how well it's worked out. And I think, if we can identify any of these problems, maybe we should consider doing another classification using slightly different seeds or different training areas, or however we've come to this point. But then that doesn't tell us how good. Let's say we've not had any of those problems, but how good, we can't identify any of these histogram issues, or it doesn't prove anyway. We've made several attempts, and there's always an issue somewhere. But now we want to say, well, how good was our classification anyway? Maybe it's good enough. How good is good enough? Well, that's another matter. But how do we even get to that point where we say, let's put a number on this? So the best thing we can do, the thing we want to do in most cases, is something called ground truthing. What that means is that we go out into the fields, that place in the image, and we say, right, what do we got here? We look around us, we say, this is definitely spruce forest. It's dark, it's full of mosquitoes and lots of spruce trees. So it's definitely a spruce forest. There we go. That's a ground truthing point. And then you move to the next ground truthing point. And these ground truthing points are randomly assigned. This is quite important because we want to avoid any bias from us just finding nice convenient points, or where we think our classification has worked best. It's randomly assigned. Preferably we should be doing this before or at the same time as the image was acquired, so that we're not having any problems with, say, the forest being cut down between us being there and the image being taken. And this ground truthing is considered as sort of gold standard. You get the best data. The problem is that it's not always possible or practical or cheap. It takes time, costs money. So yeah, but what you can, if you can't do this, then there are other methods that, but then you can also do other methods as well as ground truthing. So you start with your ground truthing and get some data, and then you can do this other category where you take other information, or you return back to the original image, satellite image or aerial photograph, and you use your fantastic brain to classify information at these random pixels, randomly assigned pixels. So, well, what is that there? That is this thing. That is spruce forest, that is a field, that is water. And you make the classification using your intelligence to do that. And then we can compare that with what the computer came up with. So, and we can combine this with the ground truthing if we have ground truthing. If we don't have ground truthing, then we just have to find out truthing data from elsewhere. We may also have other sources as well, just to help. But what we do not do is use the classified image that we've made to help us make the judgments. That's not on. We have to be doing this from our brains or from secondary, so other sources. But once we've done this, I've gone through all of these hundreds. We really do need a lot of pixels for this, really, if we're going to be proper about it. We need to assess a lot of pixels to say whether they were, what actually the class is of that pixel. So we've looked at a pixel on the satellite image, and we say, well, that's water, that's a field. And what did the classification come up with? We can compare it with that. And what we can end up with then, when we compare all of these pixels that we've actually assessed, is an error matrix or a confusion matrix or contingency table, a few different names. So let's just run through this. What does this mean? So in this case, we have 100 pixels or percentages, we can say here, if you like. But even though we have 10, this is 100 pixels. Let's say it's 100 pixels, and in the image we've got the classes that came from the image, from the classification, and on the side here we've got our ground truthing or our truthing data. So we've gone out and we've visited the sites, and these are the classes that we identified at those pixels. And we can see this diagonal going down here. We were both in agreement. 12 pixels were both classified as water. 55 were classified as water in both methods, by the classification done by the computer and when we were out in the field doing it, or when we manually classified the pixel. And 54 were forest according to the computer, and 54 were forest according to us, and so on. When we read down here, water, we have all of these, we have 20 pixels of water here. They were classed as water by the computer. But when we went there in the field, yeah, we got 7 of them were actually forest. 1 of them was grass. Right, so that's an error. We also, when we visited, we went to a number of pixels that were water. When we got there, we thought, well, that's water. But the computer actually classified 2 of them as being forest. And none of them were classified as grass. There was a bit of confusion there. Some that were water, the computer thought were forest. So that's 2 different kinds of errors. And we have what's sometimes called user accuracy and producer accuracy. So the idea is that how good was your classification? What did you do? How well do you trust your information when you produce it? Or you as a user, when you're going out there in the field, you've got this map. How good actually is it? You know, what are you likely to find when you get there? So there's these 2 different concepts. So we can evaluate things in these 2 different ways. But the overall accuracy, which we can see here, is 84%. Generally speaking, that's our accuracy, even though this classification here might suggest otherwise. In total, when we sum things up, we get this. But we can see that certain categories tend to be better than others. We've got a 92% accuracy here for the forest. That's good. But in total, and if actually we're mostly interested in this forest, then maybe that's good enough for us. It depends. And where we draw the line on this, what's good and what's bad, that again is another question that we have to deal with separately. But we have these tools at least to get us to this stage.